Finally, we're going to talk about some special trees, and then we will get into binary tree traversals. And so in the three different types of special trees, any binary tree is restricted to having 0, 1, or 2 children for each of the nodes. But we can have a certain situations for trees that will be especially helpful. So for a full tree, every node has 0 or 2 children. So every node has 0 or 2 children. What would that look like? Well, that is a full tree. And if that has 2 children, that's also a full tree. If I were to do this, then it's not a full tree. Because if I have one child, I've got to have the other child. But I can certainly do something like this would also be a full tree. So we just check to make sure they have either 2 children or no children. No children here, 2 children. 2 children, no children. And as long as we have that, then we have a full tree. That has some special applications. Then there's the idea of a complete tree, and we'll be coming back to this. We will be coming back to this when we get to heaps, so pay special attention to what a complete tree is. The leaves are filled up. In raster format. Meaning, if we go through like a typewriter, ding, ding. So, for example, this is a full tree. Why? We filled up everything in level 0, then we filled up everything in level 1, and then we go down to level 2, and we fill it in left to right order, meaning we kind of raster around, so that if we have leaves, well, then everything in the earlier generations would be completely filled up. So this is a full tree. This is a complete tree. That's a complete tree. This is not a complete tree. Why? Because there's a blank here. But this here is a complete tree. So the idea here, and I'll draw in a couple more. So this is complete. That's a complete tree. And why is it? Well, because it's filled up as you run through it like a typewriter. And there can be blanks in the last row, but they have to be on the right. You have to fill up the lefts first before the right. Also, I wanted to emphasize, this is not a full tree. The full tree transgression comes right here because we only have 1. So this is a complete tree. Now, if we mash together the full tree and the complete tree concepts, we can get the perfect tree. A perfect tree looks like this, or like this, or meaning it's completely filled up and all of its last rows are complete. So this is both full and complete. So it's a perfect tree. So we have all levels filled up. And as you can imagine, this gets harder to draw. So that's also, these are all perfect trees. The complete tree will come up again when we talk about heaps, okay? And so then, let's talk about traversing trees. When we traverse trees, we can do so in 3 different formats. We're going to be talking about binary trees, but this works for any type of tree, works for the general tree. So the idea here is that we want to, let's say, print out all of the values in the tree. But we do so in a particular methodical way, and we have three choices. So with pre-order traversal, we first print or service the current node. Then we pre-order traverse the left child's tree. And then we pre-order traverse the right subtree. Okay, what does this mean? What we do is, this is going to be a recursive function here. When we get to a node, we'll print out its data, then we'll call the function on the left child, and we'll call the function on, after that, on the right child. And when we do this, the child, remember, is the same thing as a tree. And so if it has no children, we don't have to do anything, but we're going to recursively go through. So for example, when we have a tree, let's set up a tree here. ACH. Okay. We've got, and I'm going to draw it without the circles. So if we've got A, C, H, okay, so if the tree isn't too big, it's okay to do it as a human by hand, but it can get pretty tricky. These recursive algorithms work great for a mechanical computer, for a electromechanical computer, but we have to play to be the computer as we follow through. Remember, we print the current node, then we do a pre-order traversal of the left subtree, pre-order traversal of the right subtree. Well, for now, let's just think about doing a pre-order traversal. What would we do if we were just going to do a pre-order traversal of this? We get down and we'd say pre-order traverse this small subtree. Well, the first thing that we do is we print out the current element, then we do a pre-traversal on the left and then a pre-traversal on the right. So this would print out L, M, and then X, and it would so this would print out L, M, X if we were to do it. We think to ourselves, what would happen if we would go up one in the tree? How would this happen? Well, this would print out the R, then it would recursively do a pre-order traversal on this subtree, which would give us LMX. So this, if we were to print this R, we would have said R, then L, then M, then X, and so forth. So we'll think about then how to do the entire tree. So I won't write it down, but you think to yourself, okay, what's going to happen? A is going to print out. Then we go to the left subtree, and we have to pre-order traversal this. So it'd be C, then H, then nothing, and it would go back up to A, and then it would move on down. It would print out the Q, then it would print out nothing, and then it would go down and do a pre-order traversal here. So it'd print out the J, then it would go down, print out the R, print out the L, print out the M, print out the X, go back up to the R, go back up to the J, there's nothing to print here, and then we'd be set. Okay, so what do? We go to the A to the C, got A, we do C, and then we go down to the H, then we get to the H, and we'd go back up to the C, and we'd go down to nothing. So then we'd go back up to the A, and now we go over to the Q. So then this is going to be a Q, then it's going to hit the J, then it's going to hit the R, then it's going to hit the L, then it's going to hit the M, and then it's going to do the X. And that would be a pre-order traversal. Okay, what about an in-order traversal? In-order traversal just switches those. We're going to and then we're going to traverse right. Okay, now that's not going to cause too much of a problem. It's just that we have to remember that we have to move through the left subtree from its entirety, then we print out A, then we traverse the right, we traverse the left, then print out A, we traverse the right, and then we're done. Okay, but we do so in a regular format, in a recursive format. Okay, so what do we need to do in order to traverse this in order? Okay, this is where it gets kind of tough. So we're going to, first of all, we go to A, but we don't print right away. We go down to C, but we don't print right away. We go down to H, and it doesn't have any left children, so we print H out, and then we go to its right, and then it's null. So we go back up to the C, at which point we print it out. Then we go down to the left subtree, nothing. So we would go back up to the A, and then we would print that out. So trying to keep both of these in view, I'll put it over here. We'd be at the A, then we'd go down to the C, then we'd hit the H, then we'd go back up to the C, then we'd hit the A. Now we got a long road ahead of us to traverse all this here. So first of all, we go down to the Q, but we don't print it right away. Instead, we print out the left subtree, which is, in this case, there's nothing there. So then we print the Q. Now we have to traverse the right subtree. So we don't print the J right away. We get down to the J, but we have to print all of the left, then print J, then print null's subtree here. So then we'll go down to the R, then we'll go down to the L, then we do the M, L, X. Then we go back up to the R and we print it out, and then there is nothing to the right of the R. So we go back up and then we print out the J. We go back, we see there's nothing on the right subtree to print for J, and then it would go on through. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 letters. We should have 9 letters here, 3, 3, 3, and we're good. Now we get a different sequence when we traverse it in different ways. Your in-class exercise for today will be to do a post-order traversal. So you'll do a post-order traversal on the tree that you make. You'll make the tree manually, and then you'll run your code on the expected input and output. Okay, so for post-order, I'll just go ahead. You can probably imagine we traverse left, we traverse right, and then we print node. Okay.